Hello, I am Professor S. Shankaran in the Department of Metallurgical and Materials Engineering.
Creep mechanisms involving dislocation and diffusional flow. So we just looked at the previous two cases as an independent mechanisms. But normally materials undergo creep accompanying several mechanisms together. So one such popular mechanism is creep mechanisms involving dislocation, glide as well as diffusion flow. Let us see. The linear dependence of creep rate on the stress for a diffusional creep is not observed under the conditions of moderate applied stress. Instead, the value of the stress exponent m prime in the primary equation. What is this primary equation? If you recall, before even discussing all these mechanisms, I just showed one basic equation for the all type of creep mechanisms and power law equation. So that is what I'm just mentioning here as a primary equation, and where the stress exponent m prime ranges from about 3 to 8. Under these conditions, creep involves dislocations as well as diffusional flow. The dislocation creep and the power law creep, PLC, it's called power law creep, being the most common. The term power law creep arises because the creep rate varies with the stress to a power greater than unity. Very important. So the power law creep also, coming to this dislocation, creep mechanisms, because the stress, the creep rate varies with the stress to a power greater than unity. A number of mechanisms have been proposed for PLC, that is power law creep. There are so many mechanisms have been proposed. Two among them are solute drag creep and climb glide creep. So there are several mechanisms reported in the literature, but we just look at these two, which are quite familiar to us. Solute drag creep. What is solute drag creep? First, let us look at this terminology. Creep rate formulation. Epsilon dot SD, solute drag, is equal to ASD times D solution, or solute here, because we are talking about solute, diffusion term of solute divided by B square into sigma by G square into sigma omega by KT. So what is new in this? Almost everything is known to us, because every creep rate has got some constant depending upon the specific microstructural geometry, and which is taken into account, right? Whatever the specific microstructural features. Here, what is the microstructural feature we are going to consider is the solute drag. That means the interaction between dislocation and the solute has to be taken into account. Any geometry where the involvement of solute interacting with a dislocation. This we have already seen in the several occasions. In one of the primary expressions we have seen in the strengthening mechanisms, and also dislocation dynamics we have seen how the physics is the same. So that is what I am trying to say here. The microstructural feature and the physics are the same. Rest all the common other parameters, like you have sigma by G, this term, and then this sigma omega by KT term. They're all familiar to us. That's what I'm trying to say. So the other mechanism, that is dislocation climb glide creep, is it is not that well understood as compared to solute drag creep as per the literature. But then the physics is not that different, because we are talking about the climb glide. So the dislocation interaction, that physics is much more familiar to other mechanisms. So what is involved here? You can see that epsilon dot Cg is equal to A Cg times dl divided by h to the power 3.5 into m to the power half into sigma omega by kt. So what this particular model considers is m, that is a number of dislocation sources per unit area. So, for example, the most familiar dislocation source is a Frank-Reed source, which comes as a loop and then it opens, right? So, such loops it considers, that is a number of dislocation source per unit area, that is m, and h is the distance between each sources. It could be on the same different level of plane, so that is h it considers, and the L is the distance of the loop. So that is what it is. So it involves these parameters. So basically it takes care of all the microstructural scale and its parameter. The rest is again the stress assisted energy term and the thermal energy term. That's the ratio that is common. So this keeps coming. Okay. So all the power law creep models have in common a correlation between a microstructural scale and applied stress that results in the greater stress dependence of climb glide creep compared to the diffusional creep. So this is very important. All the power law creeps models, whether it is a dislocation glide or a dislocation solute drag, and so many models have been reported depending upon the material system and also the specific conditions. Okay, so they are all emphasizing one point primarily is the greater stress dependence of climb glide process, creep process, okay, as compared to diffusional creep. So the stress dependence is the primary focus here. In spite of the apparent diversity of the formulations of several creep rates presented in this section, all of them can be expressed in a similar form. What is that? Yeah, so most of the mechanisms can be represented in the general form like this, the creep rate, that is epsilon dot is equal to A times d by omega to the power 2 by 3 sigma by g to the power m prime sigma omega by kt into b by d to the power n prime. In the equation, the last three parameters on the right hand side are dimensionless as a constant a. So similar to a, so these three parameters also dimensionless. The d by omega to the power 2 by 3 has a units of per second, that is, it has units of creep rate. The ratio sigma omega by kt is the ratio of mechanical to thermal energy. This we have already seen. The parameter b by d to the power n prime, where b is the Burgers vector, b is also equal to omega to the power 1 by 3, represents the grain size dependence of the creep rate. The term sigma by g is the ratio of the applied stress to the shear modulus. This ratio is important in determining the rate of power law creep. So this is, you can see that m prime, this is the stress exponent. Okay, so that is what it says. The ratio is important determining the rate of power law creep. So what is the significance of this stress exponent and other n prime and all that? You can see that it is now tabulated here for a Nabarro-Herring creep of mechanisms, which is favored by high temperature, low stress, and fine grain sizes. You have the value of A is 7 and M double prime is 0 and N prime is 2. It is a small n, it is not a capital N. Small m and small n. There is a typo here. For a Koebel creep which is favored by low stress, fine grain sizes and temperatures less than those for which Nabarro-Herring creep dominates, you see the value of A is 50 and M double prime is 0 and N prime is 3. So power law creep on the other hand, which is always favored by very high stresses, we will talk about the A value in a minute, but then you see that it varies, M prime varies between 2 to 6 for a power law creep and N prime is 0. The terms A and M double prime are strongly dependent on the mechanisms controlling power law creep at the substructural level. So kind of, it heavily dependent on the microstructural features that develops during this deformation. So that's what you have to understand that. Values of A can range from several to several million. So it is quite complex there. Nothing can be predicted as such. So this is quite complicated because of the so many parameters involved, right, depending upon the deformation condition. So this particular slide gives a kind of summary of all the creep mechanisms. So any creep mechanisms you think of, or any new material, always a combination of mechanisms takes place, right? It's dislocation, glide, and then diffusion and power law. So all of them can happen in a sequence manner. So you need a very comprehensive idea about the creep rate. So that is why this equation is useful. So this is a general form. Depending upon the situation and the microstructural scale and what dimensions this, so that will be taken care by this first term. The rest of the three terms will be almost same for the material involving different mechanisms in a sequence or parallel, whatever it may be the case. So it gives you an overall idea about the creep rate in different materials. So now we will look at something called a deformation mechanism maps. So we are looking at different mechanisms. How do we comprehend the idea? Okay, how do we summarize? You see, this plot is quite popular plot, deformation, which is ln sigma, that is stress normalized with the shear modulus G, and the temperature normalized with the melting point, that is homologous temperature. And then you see all the deformation, the creep mechanisms are demarcated with the different boundaries. So dislocation glide and elastic region, and the temperature T1 and T2, you have a Koebel creep, a Navarro-Pekin creep, and the relatively high stresses and high temperatures, you have dislocation creep, and very high stresses and relatively low temperatures, it's only a dislocation glide. So it gives an idea what kind of mechanisms one can look at. Suppose if I trace this, if I start deforming this at this temperature, as I keep on increasing the stress, how I have to overcome, or I will come across different mechanisms, creep mechanisms. So it gives an idea about it. A schematic deformation mechanism map. The axis of the map are homologous temperatures and the stress normalized by the shear modulus. The stress temperature combination determines the primary deformation mode. Obviously, the stress temperature combination is the key for a creep. At the boundary lines, the deformation is due equally to two mechanisms. So any boundary will have the possibility is two. Okay. Two or even to three mechanisms. There is a triple junction, then you have possibility of Koebel, Navarro-Herring, and then other. Or here it is very clear. It could be a dislocation creep, or it could be Koebel, or it could be Navarro-Herring here. So it is completely in this triple junction. It is a elastic deformation. The deformation mechanism map has axis of homologous temperature. But okay, this is already known. Several deformation mechanisms regions are included in the figure. These are all dominant deformation mechanism at the stress temperature combination for which they are listed. The lines separating the regions represent stress temperature combination at which two mechanisms contribute equally to the material combination. This also we have seen. So this is again a redundant statement what I have already shown here. Another very interesting information about this is people have looked at beyond the influence of stress and temperature, and here what you see here is the different grain sizes. Okay, so for different grain sizes, how this the regions get modified. Okay, along the This is, we are talking about 100 micron to 32 micron and then 10 micron, how this boundaries are get changed. So that means the grain size significantly influences the creep behavior. Of course, it is for the given stress and temperature combinations. So that is something you have to appreciate. A deformation mechanism map depends on the grain size. Finite grain sizes expand the regions of diffusional creep. So what is being consumed, the region wise, is the diffusional creep is getting reduced, that the region is getting reduced. An alternative formulation of a deformation mechanism map has the axis of normalized stress grain size at a specific temperature that is given here. This is for one temperature. Then what happens? The dominant creep mechanisms are identified for various stress grain size combinations. So here we are talking about a grain size versus stress, and you can see that how the different mechanisms will play a role. So this is basically for a constant temperature. You can look at the what are the mechanisms. So this is another way of looking at which creep mechanism will dominate as an influence of grain size. So now we'll come to a very important parameter, the engineering estimates of creep behavior. How people use the engineering data, the creep data. As I said in the beginning of the creep class, so the steady state creep that is being, that is the design parameter, right? So how it is being used, we have to just see. The fundamentals underlying the extrapolation techniques are contained in the empirical equation relating strain rate to the stress and the temperature. So what is that? Again, I will refer to the basic equation, the stress exponent equation, strain rate, the very basic equation we are going to take. On taking logarithm, natural logarithm from both sides of that equation, it can be written like this: ln epsilon dot is equal to then minus QC by RT plus G as a function of sigma, where G sigma, a function of applied stress, is the natural logarithm of all terms on the right hand side of the equation excepting the term exponential minus QC by RT. Stress rupture tests in which the time to fracture or rupture TF is measured as a function of stress and temperature are commonly performed for short time material evaluation. This point we have discussed in the beginning. Provided TF is inversely proportional to the steady state creep rate, we can substitute TF is equal to K by epsilon dot in that equation. So we can rewrite this ln TF minus ln K plus G as a function of sigma is equal to QC by RT, or T into ln TF plus G sigma minus ln K is equal to QC by R. As the QC by R is a material constant, the terms on the left hand side of the equation which are related to the Larsen-Miller parameter, it is popularly known as LM parameter, or this is called Larsen-Miller parameter, can be used to assess the material creep resistance. The parameter is frequently expressed as Lm is equal to T into log base 10 of TF plus C. So this is the Larsen-Miller parameter. So how is it being used? That is the question. Where log TF represents the logarithm to the base 10 of TF and it is expressed in hours, and C is an empirically determined constant. So now we look at the stress versus TF, that is fracture time in hours, for different temperatures. You can see for a particular alloy system, a commercial alloy system is given here in this illustration, and then stress fracture time plots for an iron-based alloy S590 at different temperatures, and then the Larsen-Miller master plot for the data of A. The abscissa is the parameter t into c plus log tf. So this is LM parameter, and this is stress. So what you are seeing is from these plots, then you will be able to calculate the time required to fracture. The diagram permits fracture times to be estimated for a variety of stress temperature combinations. So this is one very crude way of, I mean, very simple. I would say why I'm saying crude means because there are so many other things, complications will take place because this is only an empirical relation. So it gives a rough idea about the time to fracture for any high temperature material. So this is quite this is one way of looking at it, but there are several other methods, advanced methods. But my intention is not to get into all the details because it is completely out of the scope of this course. But then at least how, since I said that the creep rate is a design parameter, how people try to use that basic equation to arrive at the Larson-Miller parameter. So that was my only intention, not to do any other calculation or getting into the details of the advancement of this estimation. This is very old and reported in most of the texts. So I will stop here. We will continue on the creep behavior of other amorphous and semi-crystalline materials in the next class. Thank you.